All right. Just as with line integrals, one of our primary examples of a line integral involved vector fields. We calculated work by integrating a force field dotted with a unit tangent vector. One of the main applications we're going to look at for surface integral is something called flux, and that is also going to involve vector fields. Now, I know a number of you are taking physics classes where you're looking at electricity and magnetism, so you're studying flux in that context. We will talk about electric flux when we're integrating an electric field over a surface doing a surface integral of an electric field. I'm going to start though with fluid flow. So I've got some liquid and it's flowing. And so I'm going to have S, which is an oriented surface, and I'm going to suppose that that's a permeable surface. So if my fluid flow, let's say, is a river that's flowing, and I were to put my surface into that river, and it's permeable, so that if here's the surface, the water can flow through it, okay? Then I can sort of measure how fast the water is flowing through that surface. I'm going to start with that example because it's a lot easier to wrap our brains around what flux means in the context of fluid flow. Once we've established what flux is in this context and how we evaluate it, we will return to the notion of electric flux and try to wrap our brains around what that actually means. Okay? But I'm going to suppose that we're looking at fluid flow. So I'm imagining that I've got a river. I've taken my permeable surface. I've put it into the river. And if S is oriented, we're going to have N being its principal unit normal vector. So if I had my surface here that I put into the river, and this was the principal unit normal vector, then water flowing this way would count as positive flow in that direction. It's possible, however, that the water is actually flowing this way, and now I can say that's negative flow. Okay? And it's possible that I've got the water sort of spinning around so that some flows this way and some comes back this way so that there's some cancellation. But the flux is essentially going to allow me to calculate. I could either calculate the volume of liquid that's flowing through per unit of time, or what we're going to actually do is scale our velocity function by our density function so that we can calculate the mass that's flowing through per unit of time. So I'm going to have a vector field V, which is my velocity field. So the units for that are going to be units for distance divided by units for time. I've just chosen to say, let's suppose that those are meters per second, because sometimes looking at what the units are can help me figure out what's actually being measured. It would be totally fine to use other units for length and other units for time, but this is just the example I'm going to be working with. Okay. Now, rho is my density function for the fluid. So that would give me the mass per unit volume. And so I've said, let's let our units for that, let's use kilograms for mass. And if we're using meters for distance, that determines that I better be using cubic meters for volume. Okay, so this would be the units for that. I'm going to put these two together. I'm going to take this real valued function and use it to scale this vector valued function. So I'm going to form this vector field that I'm calling F, which is rho times V. Now, what's that actually measuring? Well, for that I'm looking at the units. Rho is in units of kilograms per meter squared. V was in units of meters per second. So one factor of the meters will cancel. The units for F are kind of weird. They're kilograms per square meter per second. Okay. So that's essentially telling me how much mass is flowing through 1 square meter of surface every second. Okay, so it's measuring a rate of mass flowing through the surface. If I didn't scale this, and it's possible to do that and it would still be called flux. If I just worked with the velocity field, then flux would just be calculating the volume per unit of time. We're going to set it up so that we're going to work with F, which is density times velocity, so that our flux is going to be integrating a function that's related to this, and that way it's going to be calculating mass per unit of time that's flowing through my surface. Okay? Turns out what we're going to end up integrating is we're going to look at the surface integral of f dotted with that principal unit normal vector. We'll see in a moment that's going to be the component of this that's actually flowing through the surface. Okay. And I've said that's going to be measuring mass per unit of time that's flowing through the surface F. Its units are going to be kilograms per second. I can actually work that out because this is just a component of, it's actually the signed magnitude, I should specify. That's going to be the signed magnitude of a component of F. Its units are going to be the same as F. And we'll see that in a moment. Right now I'm just sort of asserting that, and if you're sort of like, why? That's okay. We're going to see why in a moment. Okay? But the units of that are the same as the units for F. So that would be kilograms per square meters per second. And when I'm integrating with respect to surface area, I would be measuring in meters squared. So those are going to cancel, and the units for flux here are going to be kilograms per second. Again, if I didn't scale, and some textbooks define flux to be just what you get if you integrate velocity. If I wasn't scaling by density, the units would be meters cubed per second, and I'd be measuring simply volume of liquid per unit of time that's flowing through my surface. Okay, so that's our basic problem. We want to try to calculate this sort of thing. So, how do we do that? Now, I've told you this is what we're going to be integrating. I'm going to be sort of deriving why that is what we're integrating, and in the process, I'll be able to explain why that has these same units and how that is what I referred to it as the signed magnitude of a component of the vector field F that we are trying to integrate, or that we are trying to work with. we're not integrating the vector field, we're integrating F dotted with N. Okay, so here's my surface S. Now, that looks like a one-dimensional curve. What I'm meaning for this to be is this is a cross-section that we're looking at. So it's coming out from the board. So it's as if this is my surface, like so, and we're just looking at a cross-section that we have here. Okay. Now, I've immersed that in this river where I've got this scaled velocity field, scaled by the density function, so that we're incorporating mass and not just amount of liquid. Okay. So, at every point on this surface, there's some vector F that's associated with that point at that particular surface. So obviously the vector field exists on either side of the surface as well, but I'm going to be concerned with the vector field as it is on that surface. Okay. And I'm trying to calculate the mass per unit of time that's flowing through this surface, where if it's flowing in this direction, I'm going to count it as positive. If it's flowing in that direction, I'm going to count it as negative. So flux is a signed quantity. Flux can be negative, and if flux is negative, it's just saying more stuff is flowing in the negative direction than is flowing in the positive direction. Okay, as I set this up, I am going to go through my usual 4-step process. So I am going to chop things into little pieces. Okay. Now I'm going to just write out that I'm chopping this surface. I will ultimately, of course, be evaluating this by parametrizing the surface. But I'm going to just write out that I'm chopping this surface into little pieces. That might be a chopping that's induced by working with a parametrization. So each of these little pieces here, I need to remember that actually represents a little patch of surface that I'm going to have. I just sort of looked at a cross-section of things here, okay? But realistically, I would have little patches of surface like so, okay? And so when I'm ready to approximate of course, every point on that little patch of surface is going to have a vector in this vector field F associated with it, and those vectors might vary. They might have different directions, they might have different magnitudes. Oh, how inconvenient is that? I think we should go into denial. So, we're going to pick a representative point, and we're going to calculate the vector field at that particular point. So if I call this Pij star, that's my representative point from the ijth patch of things, this would be F evaluated at Pij star. So I'm going to treat it as if my vector field F is constant at that value over this entire thing. Okay. Now, I want to try to calculate what's actually flowing through this surface. Okay. And if I take a look, I think it's actually easier to see that if I look at this representation. So, looking at this, if this was my little patch of surface, just imagining that it's coming out towards us, and this was my Pij star, and this was my F of Pij star. But this right here is my normal vector at that particular point. That's the principal unit normal vector. So this is determining what's going to be flowing in the direction. You know what? I can improve upon that because that doesn't look like it's actually normal to the surface. So let's fix that. It's probably going to be easier to see if I choose Pij star to be sort of in the middle. So I think I'm going to do that on this picture. Pij star can be any point. It's going to be easier to visualize what's going on, I think, if I put it somewhere in the middle. So I'm going to do that. And here, this would be the normal direction to the surface. So let's let that be my principal unit normal vector at that particular point. Okay. Now, if I look at F, I can actually write F as a sum of two vectors. If I project onto the principal unit normal vector, then I can write F as a sum of this vector plus this vector. So this right here would be the projection of F onto N. In the interests of time and writing energy, I'm just going to write F, understood that it's F evaluated at that particular point. Okay. Now, that is definitely contributing to stuff that's flowing through the surface. This, on the other hand, if I slide it over here, because that's really where it's happening, that's tangent to the surface. So it's that component really isn't contributing to anything flowing through the surface. That's just moving right along the boundary of the surface, not actually crossing it. So this is the component of F that's going to be contributing to stuff flowing through the surface. Now, as I've drawn it, it's a positive multiple of N. If my F had been pointing in this direction, I would be getting a negative multiple of N, and that would be contributing to negative flow, or flow in the negative direction through the surface. All right, this video has been going for a little while, so I'm going to pause it here, and we'll pick up in the next video with this derivation.